Okay, I'm going to continue on the Chapter 7 applications and extensions of the integral, and I'm going to do 7.2, the average value of a function. How do you find the average value of anything, or how do you find the average of anything? Well, usually you add up all the numbers and divide by the total number. So if I averaged your tests, I'd be adding all the test scores up and dividing by 32 if there's 32 students, and that would give me my numbers. So that would be what you would do to find the average. So the average value of a function is very similar. One thing I want you to note is this is started on page 491. The sum gives an approximation to the average value. As the norm delta goes to 0, it provides a better approximate to the average value of the interval from A to B, the closed interval from A to B, which leads us to the average value function formula. The formula is the average value equals 1 over b minus a of the integral of a to b of the function of x dx. Okay, let's look at example 1. It's pretty simple, really. Find the average value of the function x cubed over the interval 0 to 2. So 0 is my a, 2 is my b, and I'm going to put that in the formula of the average value. So the average value formula is 1 over 2 minus 0, integral from 0 to 2 of x cubed dx. I go ahead and integrate that. That's going to be x to the 4th over 4. But I have the 1 over 2 is 1/2 times x to the 4th over 4 from 0 to 2. Don't forget the 1/2. That's important. The 1/2 times 2 to the 4th over 4. I crossed out one of the 2's because of the denominator. 2 goes into that one. That 4, so I crossed out one of those. So I now have 2 cubed over 4 minus 1/2 times 0 to the 4th over 4. And 2 cubed over 4 is 8 over 4 or 2, the average value. Note, most of the time, these questions always say average, something to find the average. So you'll know to use this formula. There's going to be several more formulas that you're going to have to use that aren't going to be average, so they won't say that. Now, there's a geometric approach to figuring out this. So the geometric approach is, see the 1 over b minus a is on the right side of the equal sign? The geometric approach puts the b minus a on the left side. So it's like length times width of a rectangle, and you're finding the area under the curve, which you did in the last chapter. So b minus a becomes this width, and the height becomes the integral of whatever your AVA times your interval. So the approach is b minus a of the average value equals the integral of a to b of the f of x dx, or the area under the curve. All right, example 2. Suppose the current world population is 6 times 10 to the 9th, and the population every t years is proved to give approximately at 2% growth rate, according to this law. The p of t, that's a little t, equals 6 times 10 to the 9th e to the 0.02 t. That formula should look very familiar in the last chapter, what we did with our bacteria formulas. What will the average world population, again it says average world population during the next 20 years. So the average is going to be from the 1 over 20 minus 0, or from 0 to 20, of 6 times 10 to the 9th e to the 0.02 dt. Now, I noticed real quick that 6 times 10 to the 9th is a digit, so I took my 6 times 10 to the 9th out over the 20 that was already out. Notice that's a direct on the numerator. And then I could just integrate e to the 0.02 dt. And e to the 0.02 dt is itself over the derivative of the numerator, if you put that as a u equals. So 6 times 10 to the 9th over 20 times e to the 0.02 over 0.02 from 0 to 20. If you put your 20 in and your 0 in, you have the 6 times 10 to the 9th over 20. I decided to keep that on the outside of the parenthesis, or the quantity there, and then do my numbers on the inside. E to the 20 times 0.02 over 0.02 minus e to the 0 times 0.02 over 2. Notice e to the 0, again, is not 0. E to the 0 is 1. So this becomes e to the 0.4 minus 1 over 0.02 times this 6 times 10 to the 9th over 20. Note, we reduce this also. This is 2 times 10. The 2 went into the 6 3 times. I took one of the 10s away, and I get 3 times 10 to the 8th times the quantity of e to the 0.4 minus 1 all over 0.02, which does equal, if you stick it in your calculator, 7.38 times 10 to the 9th. Average world population in 20 years. Okay, I'm going to get the second board out. Now, what I'd like to mention is that is literally all that's on 7.2, is the average value. So your assignment is your 7.2. I am going to continue to start teaching some of 7.3 because it's a very long assignment. So 7.2 assignment is page 492, 13579, 13, 14, 15, 16. That is your assignment for tonight. This is extra, but it won't hurt you to go on to start 7.3 because it's a very long section. All right, so I'm going to start 7.3 now. It's on continuous probability functions. So it gives a lot of wording. It talks about random variable is a function that assigns a numerical value to each outcome of sample spaces. So you have to know what a random variable is first. Then it talks about discrete random variable. A discrete random variable has a finite number of outcomes, as many outcomes as counting numbers. Discrete means that it stops. And the third one is continuous function random variable, has values that consist of the entire interval of real numbers, and it is continuous. We'll talk about some continuous things in a few minutes. Now, the probability function has as its domain the value of the random variable and its range, the corresponding probability. So you're going to have that in a few minutes. So I'm going to let you write that down for a second. They're also all in the book. Let me look at what page. On page 494. So if you don't want to write this down from the board, you can look at page 494. So I'm going to stop and let you go on. Let's go on to the example. In the experiment of tossing 2 dice, compute the probability function x equals 7, where x is the sum of the dice. Now, some of you are going to think this is very easy, and it does start very easy. It will not be as soon as we get going through everything. So the probability of x equals 7, I decided to write down all the values of how I can do 2 dice and x equals 7. On the first dice, I could have a 1, and the second is 6. And then I could have a 2 and a 5, or a 3 and a 4, or a 4 and a 3, or a 5 and a 2, or a 6 and a 1. Yes, 6 and 1 and 1 and 6 are different because they're on different dice. So how many possibilities did I have on the top? 6. When you total number of the sums, if you figured out every single sum possible, it's the 2 dice multiplied, 6 times 6, or 36 is your denominator. Now you have 6 over 36, or 1 out of 6 chance that the probability is going to be a sum. All right, that's just reviewing probability. Now this next stuff is what's going to come from the first part of your 7.3 assignment. Probability density functions. Continuous random variables like weight, arrival at a gas station are continuously changing. I'll use my weight for example. My weight is always fluctuating. I am not always 120, 130, or 140. I'm always someplace in between, and it fluctuates at all times. I don't arrive at the gas station at the certain time every single time I go to the gas station either. It's continuously changing. So they tried to make this by a distribution age chart. This is also on page 495 and 496. So if you'd rather look in your book on page 495 and 496 at this beautiful chart that I tried to replicate. Suppose the distribution by age is in the chart. The total population is 200 million. So what I tried to do is at the age of 10, from 0 to 10, it was like 30 million. And from 10 to 20, it was 40 million, and so forth. So that's the chart. We did a line chart like that a couple months ago. By putting that out, the probability values of the smooth curve, by putting the continuous connect them with the green, it's continuous probability values by a smooth curve. That's the probability density. That's what they're trying to get you to understand. Now here's one more thing. A function is probability dense if the function of f of x equals 0 on a to b. Actually, the integral from a to b of the f of x dx equals 1. This is huge. So this integral has to equal 1 for it to be probability dense function. If it doesn't equal 1, it's not probability dense. Now tomorrow we're going to figure out what that's going to do. Actually, we're going to talk about it here. It always equals 1. If not, you multiply by a k to make it equal to 1. The k will be the reciprocal of your answer. So, example 2, show that the function 356 times 5x minus x squared is probability dense from the interval of 0 to 4. So 0 and 4 are my a and b. So I put those down as the a and b. I put the 356 on the outside, and I integrate the 5. Oh, that's supposed to be 5x. My bad. 5x minus x squared dx. 356 x squared, 5 times x squared over 2 minus x cubed over 3 from 0 to 4. I stick my 4 in. 5 times 4 squared over 2 minus 4 cubed over 3 minus my 0 in, which is going to 0 out in both, times my 356. Well, if you do good math, the 356 is on the outside. I get 80 over 2 minus 64 over 3, which just happens to be 56 over 3. What happened with these two numbers? They're reciprocal because of 356, we have to multiply it times the number you get on the inside, 56 thirds, and that equals 1. That makes it probability dense. If you did not get the same fraction or reciprocal fraction on the inside and the outside, then you would have to state that k is the probability density factor, and we're going to do that then tomorrow. So that's starting on 7.3, but I will not go over that again tomorrow. Probability dense functions have to equal 1. Okay, that's all I have for today. Have a great day.